Hi everyone. Today, I'll present on IoT network architecture and communication standards in agriculture. This is a fascinating field where IoT is driving revolutionary changes in farming practices. My presentation is based on the work of Farouk et al., who explored how IoT architectures and communication protocols are tailored for smart farming. Let's get started. Smart farming leverages IoT to tackle global agricultural challenges like food security and resource optimization. IoT refers to your devices, such as your mobile phones, or to the sensors, or even the drones that they use in farming applications. From monitoring soil and weather conditions to automating irrigation, enables more efficient farming practices. So today, I'll cover two major components: the five-layer IoT architecture designed specifically for agriculture, as well as comparing communication protocols that make these systems work seamlessly. For IoT devices, normally they will have four layers: the physical layer, the network layer, the transport layer, and finally the application layer. However, for agricultural applications, a five-layered architecture for IoT devices is used, and an additional adaptation layer is introduced to this layer to enhance the data transmission over low-power networks. Let me briefly go through how each layer works. For the physical layer, this layer is where data is collected by using sensors such as the soil moisture, the temperature, and pH sensors. These sensors are designed to operate in low-power networks such as IEEE 802.15.4. At the adaptation layer, which is unique to agricultural IoT, this layer enhances data transmission over low-power networks such as ZigBee or LoRaWAN. Then moving on, the network layer, the IPv6 and RPL protocols would handle data transmission. RPL organizes devices in a hierarchical structure known as DODAG to prioritize energy efficiency and reliability. At the transport layer, this layer balances speed and reliability using TCP for critical data and UDP for faster data streams. For example, drones may use UDP for live video feeds and TCP for critical control commands. For the application layer, protocols such as MQTT are used to exchange data efficiently, even in low bandwidth environments. Moving on, let's compare two key communication protocols: long-range wireless access network, LoRaWAN, and narrowband IoT, NB-IoT. Both of these are long-range and low-power networks. However, even though they may seem similar on the surface, they actually have starkly different use cases. LoRaWAN operates on unlicensed spectrum, making use of long-range modulation techniques. It consists of several entities as shown, from the end devices to the gateway, to the network server, and lastly to the application server. The flow of the communication can be both upstream and downstream in order to transfer data from the sensors to the application server and vice versa. On the other hand, NB-IoT uses licensed LTE spectrum, which powers our mobile phones. As such, it offers higher data rates and reliability, making it suitable for urban farming practices, with features such as power saving mode and extended discontinuous reception, which allows it to balance uptime and energy use. To compare them side by side, we can see that even though LoRaWAN and NB-IoT both are long-range and low-power options, there are many differences to both. The data rate of NB-IoT is much higher than LoRaWAN, and hence is more suitable for applications where data rate is preferred, such as in urban settings compared to rural settings. In conclusion, IoT technologies are transforming agriculture, enabling smarter and more efficient systems. Understanding the nuances of IoT architectures and protocols is critical to optimizing the applications. LoRaWAN and NB-IoT are both vital tools, and their selection depends on factors such as geography, cost, and data requirements. Thanks for listening.